Good afternoon, everyone. I'm Davide Bacco, and I'm working at Technical University of Denmark. I slightly changed the title of my work in a sense that I will talk a little bit more on what we have done during these last 2 years regarding high-dimensional fiber-based quantum communication. That's the outline of my talk, so I will introduce the Spock Center. This is the center where I'm working. I'm going to talk about fiber-based quantum distribution and quantum communication with qubits for both multi-core fiber and OEM fiber. And then I will highlight two applications, so as a QKD for quantum key distribution. And in the end, I will make a comparison between high-dimensional quantum key distribution and multiplexing of single keys. So first of all, I'm working at the Spock Center. That's for silicon photonics for optical communication. It's a center funded by the Danish National Research Foundation. And the aim of this center is to find solutions to the major challenges of communication in terms of security, energy, and consumptions, and capacity. It's led by Professor Oxenloe, and it's divided in 5 flagships. In particular, it's divided in advanced multiplexing, information theory, silicon chips, photonic frequency comb, quantum communication, and nonlinear devices. Within quantum communication group, I'm working together with Jan Hong Ding, senior researcher, and we have 2 PhD students. So we have seen during these days a lot of very nice presentation about quantum communication through satellites, also the longest QKD distance reachable on a fiber link. And also, if you look at the state of the art that have been demonstrated also underwater quantum communication on a few meters demonstration. But most of these experiments has been performed with a qubit case. So we are considering a qubit transport through a fiber, free space, or underwater channel. But what about if we consider quantum communication with qubits? Are we gaining something? Is there something better? So the first answer is yes, in a sense that we can increase our thought information efficiency. We can encode more than one classical bit within one photon, within one recurrent pulse. And then it has also been proved that qubits are more robust against noise. And we have also reduction on the cloning fidelity for this dropper. And then we are gaining also in the efficiency and flexibility in quantum computing, quantum computation. What are the degree of freedom that can be used for generating these qubits? So we can have orbital angular momentum state, so by using orbital angular momentum modes. We can use temporal modes for our qubits. We can use frequency, so by using different frequency we can encode our quantum states, or also we can use path or space encoding. In particular, I want to highlight one work that we have done recently in collaboration with University of Bristol, Peking University, ICFO, and the University of Copenhagen, where we demonstrated that we can control with very high precision qubits up to a 15 dimension. So we have seen that there are a lot of groups working on the generation of qubits for, let's say, for more fundamental quantum physics. But most of them are not focusing on the transmission of these qubits through a fiber or through a free space. So the first idea that we had 2 years ago was try to use a multi-core fiber. A multi-core fiber is a fiber where we have more than one single core within the same cladding, and they are quite used in classical communication. They present more or less the same losses on the C-band, so around 0.2 dB per kilometer. And if you look at the crosstalk, so it means how much light you get in the other cores, we have very good numbers in the sense that we are around minus 80 dB from one core to the other. Looking a little bit for the state of the art, the maximum achieved right now is the 37 core generated and created by Fujikura in Japan, and they have more than 10 kilometer distance. But let's move back to quantum. So we want to use this fiber for quantum communication. So we use a photonic integrated circuit created and realized at the DTU to generate basically qubits, then to transmit through a multi-core fiber, and then use another circuit, photonic integrated circuit in silicon, to project and to measure our quantum bits. With this kind of systems that is basically composed by switches and phase shifter, we are able to prepare two also qubit and also qubits. This one was an experiment where we used a laser from outside, we couple into the chip, and then we transmit the view through the fiber. So as a measurement, basically we prepare the multi-line bias basis in the 2-dimensional and the 4-dimensional case, and we got 97% for the 2-dimensional case and 98% for the 4-dimensional case. Then we also implement an application of this, where we run basically a QKD protocol with the decoy states, and then we achieve a bit error rate that is below basically the bounds for the individual and for the coherent attacks. This kind of implementation, it was only achieved with a few meters of fibers, in a sense that it was very difficult to keep the stability through the transmitter and the receiver. Then we have also some problems with the switches, because it was a very slow repetition rate. And so there are many problematics that must be solved. But we proved that it is possible to transmit qubits from one place to another through this multi-core fiber. Then we said, what else can we use? In classical communication, the orbital angular momentum, it has been used for a lot of years, and also not only on free space channel, but also in a fiber channel. Regarding quantum communication with orbital angular momentum, I want to point out two particular experiments where orbital angular momentum was used for a free space link in Padova. And this one was quite useful in the sense that they demonstrated that orbital angular momentum can be useful for satellite-to-satellite communication. And then recently came out this work by Karimis and Boyd's group in Ottawa, where they transmit a qubit through an infra-city link. So, but fiber-based quantum communication with twisted photons, so with orbital angular momentum in fiber, was not demonstrated yet. What we did is that we used a special fiber that was designed by Professor Siddharth at Boston University and realized by OFS Denmark. It's a near-core fiber, and this fiber can conserve and preserve the orbital angular momentum of the quantum states. In classical communication, is well known in the sense that they use for increasing the capacity, so for increasing the data rate, and here we are reported some of the works that have been demonstrated recently. So how we generate our orbital angular momentum modes? We used a device that is called the vortex, wave plate, half plate, or we can also call it a Q plate, invented by Marucci in Naples. And basically, it allows to generate orbital angular momentum from a Gaussian beam. And a simple setup that we use to generating our qubits and qubits with orbital angular momentum is reported up here. So we have an external laser. When we carve our pulses to generate weak current pulses with a Varia optical attenuator, and then we use on-fiber switches, very efficient and fast switches, before two independent phase modulators. We prepare different polarization, and then after basically we move from fiber to free space, we can obtain orbital angular momentum within these 4 quantum states. So in this way, that's a simple setup. We are able to prepare, let's say, the computational basis of our quantum communication systems. Then we need also to work and prepare the superposition basis, and we adopt a similar systems. So we use again a laser intensity modulator, optical attenuator, switches, polarization modulator, and then we use a sort of a combination of multiple beam splitter to create a superposition of the quantum states. After this, we inject our quantum light through the fiber, and we basically transmit over the fiber, and we need to measure at the receiver side. On the receiver side, is not like straightforward to divide basically the orbital angular momentum modes. You need some kind of a special device. We implement OEM sorter that is basically a free space interferometer with 2 Dove prisms. And here I reported the results that we got with the single photon detectors. where we achieve 97, 98% of visibility. This sorter allows to us to separate basically the OEM6 from the OEM7. And after the sorting, we are able basically to measure in the two multi-line bias bases. The first basis is quite straightforward in the sense that after the sorter we have 6 OEM mode that is going in one direction and the 7 OEM mode that is going in the other direction. We basically use a PBS with some quarter and halfway plate to project in the 4 states. The superposition basis is a little bit more complicated because after the sorter and after the conversion back from orbital angular momentum to Gaussian mode, we need to make another interferometer in order to recover the sign of our quantum states. So let's move to the results. We did also here a comparison between a 2-dimensional and a 4-dimensional. So we achieved a fidelity of 98% on this multi-line bias basis with 2-dimensional and 95% with 4-dimensional. Also in this case, we applied, we did an application, so we used this system for high-dimensional quantum key distribution. And here is important, on the left we have the beta error rate compared versus time for the 2-dimensional case and the 4-dimensional case. And we are both below the different limits. So here we are below 11%, and here we are below 19%. Here we have a secret key rate for the 2-dimensional case and a 4-dimensional case. This one is after 1.2 kilometer of fiber. When we did something else, we emulate the channel, so we add some losses, and we proved that we can reach around 15 dB of losses. Probably I didn't mention, the fiber that we use is around 1 dB per kilometer of channel loss. So if you look at this plot, basically what we had is a 71% more or less of enhancement of a secret key rate. And with this kind of system that we present, we can in principle generate high-dimensional quantum state with a very fast speed. And if you look at the other systems, basically they are working with a spatial light modulator. That's one of the main problems in the sense that they cannot work so fast. Good. And after this, we also think a little bit more, and we said, but is it the best for a quantum key distribution system? So it is the best solution in order to generate the highest secret key rate at the end of my channel. And the answer basically is no, in a sense that since we have this special fiber that can support multiple OEM modes, what basically we run and we did was a parallel independent decoy states quantum key distribution run over 2 independent OEM modes. So we use L equal to 6 and L equal to 7 to propagate on the same fiber at the same time 2 independent quantum keys. Here is the setup reported. So basically it's more or less the same, but here we have a beam splitter. We don't have the switch. And we are running and measuring basically 2 keys at the same time. Here are the results that we generate. And if you look basically at the secret key rate that we achieved is higher compared to the case of a 4-dimensional. We also did the same with the multi-core fiber. So with multi-core fiber, again, we consider two single cores for one independent key and the other 2 single cores for another key. And we run with chip-to-chip communication systems. And also in this case, what we achieved is that the secret key rate is higher compared to the 4-dimensional case. So what's the take-home message? This one is a simulation of the secret key rate compared to the number of dimensions and the noise basically on the channel. If your channel is quite noisy and you cannot extract a key with a qubit, so by running BB84, let's say, or 2-dimensional protocols over the systems, the only solution is to use high-dimensional quantum state. But if you have low noise, it's way better to use a multiplexing technique in order to achieve and to increase the final secret key rate. So coming to the conclusion, we proved that space encoding qubits can be transferred over fiber. So we proved that we can transport the qubits over a multi-core fiber, but also over an OEM fiber. As an application, we demonstrate that we can achieve a high-dimensional quantum key distribution system for 5 meters with chip-to-chip QKD and over 1.2 kilometers of OEM fiber. And then we also did some, let's say, also some more measurement to understanding what is the best in order to get to maximize the secret key rate in the end. Thanks for your attention.
Okay, any questions?
Thank you very much for the nice presentation. One question I have again about the receiver. So at the moment, do you do really alternative detections in these higher dimensions, or is it still a filtering projective measurement onto one out of the many possibilities?
Basically, I can go back, or this is the entire setup of, you're talking about the OEM, right, Norbert?
Yeah. Exactly.
So with this kind of system, we are able to measure the 4 outcomes in this experiment at the same time. So that's also a difference compared to other protocols, because I mean all the others implementation they project only on one. So if we talk about device-independent protocols of this kind also of implementation, or if we need to measure, if we have a requirement to measure basically all the outcomes, with this kind of implementation we can do it. And obviously you can put basically before the sorter you can put another B splitter, and then you can choose one of the 2 bases to project the quantum states.
Okay, because it's a really important point.
Yeah, it's really important, yes. Probably I didn't stress a lot, but it is.
Okay, thank you.
Thanks, Al.
Any other questions? Follow this question. So for your OEM mode sorter, so can you go to much higher dimensions? Like what's the scalability if we want to go to maybe 8 dimension or 16 dimension?
So thanks for the question. This particular fiber allows to, let's say, to transmit 4 OEM modes with a good extinction ratio. And here we have a measurement basically of this mode, and also you have the amplitude compared to the noise level. And so right now there is one fiber, I think is in China, and where we demonstrated 17 kilometers of orbital angular momentum fiber. And the main problem of this kind of fiber is that every mode they have a different group index, so it means that they are traveling at different speed. So that's this kind of problem that we need to figure out how to compensate. In our system, see, we used 2 orbital angular momentum modes. It was easy in the sense that we delay one compared to the other, but in order to scale, we need to take into account this kind of problematics. For the scaling, I would say that there are a lot of groups working on integration or generation from integrated photonics orbital angular momentum, and there probably it's easy to have a sort of delay that we can compensate this kind of problems.
So if no more questions, let's close the section, and we thank all the speakers for the nice talk.